All right, welcome back to Physics 2A lecture. Today we're going to be talking about motion in one dimension. Okay, so to get us started, I wanted to give you guys a little bit of a background on what motion in one dimension really means to physics. Okay, so we call this kinematics, and that is the study of motion without thinking about any of its causes. Okay, so it's just purely thinking about the motion. Okay, and as we talked about before, we are looking at both scalars and vectors. Okay, our scalars are going to include our distance, our distance, time, and speed. Okay, and basically the parallel to that is going to be displacement, which is going to be sort of like distance. Okay, and we're also going to have velocity. That's going to be our change in position. Okay, and then we will have acceleration, which is going to be a change in velocity due to time. Okay, now I will go through these individually and talk about them. But what you need to know is that all of these quantities are very related. Okay, so displacement is related to velocity. Velocity is related to acceleration. All of these are related to our time, distance, and speed. Okay, so all of these quantities are very related. Okay, and this picture I have here is some people looking up at the stars and the moon. That is to signify one of our earliest types of science, which is astronomy. And that's where a lot of these observations started. Okay, so we started looking at relative motion, and all of our motion was relative to the Earth at the time. And now we're doing, different types of um, physics and mathematics with this, but we won't be talking about that quite yet. But let me go ahead and get started here. So the first thing that we need to understand is going to be displacement, okay? And especially we want to know the difference between displacement and distance, okay? So they're both position variables, okay? But here's the difference. So I have a start here and an end here, okay? Now, say that this is like some kind of lake or something, okay? And we can't just walk through the lake, okay? So we're gonna have to go around this whole lake here. So this person, he ends over here, but he started over here, this guy, okay, my lovely stick figure drawing here, and he walks all the way around this lake, okay? So that's going to be the entire distance that he has traveled, okay? So say, this is 10 feet, and then, oh, this is another 10 feet, and so forth, going all the way around, okay, until he gets back here. So that's 1, 2, 3, 4, about 90 feet. That's probably not very accurate, but that's okay, okay? So we're going to say that he walked a distance of 90 feet, but his displacement is going to be very different, okay? His displacement is just going to be a straight line from this starting point to this ending point, okay? And if we're approximating here, we can say maybe this is 10 feet, another 10 feet, so maybe he went like 25 feet. Okay, again, this is the displacement. Oh, that's terrible. You can't read that. Displacement. Okay. And this is the distance. See, they are very different numbers. Okay, so watch out for that when you're going through and trying to understand this better. Okay, so displacement is defined as follows. Okay, we are going to call this delta x. This delta Should write it over here. Delta is spelled like this, Delta, like Delta Airlines. And what it means is it's some kind of change. Okay, so in this case, we're looking at a change in our x. So a change in our position. Okay. And so then I have this symbol here, which is almost like an equal sign, but it's got 3 lines. Okay. This means defined as. Okay, so that's just what that means. So my change in position is defined as our final position, x sub f, subscript, that's what that is right here. It's a little subscript. And so we have, sorry, I lost my train of thought here. So we have our displacement, delta x, is defined as x sub f, or our final position, minus our initial position, okay? And in your textbook, it represents it this way, x minus x naught, okay? X naught, I'm sorry, that naught right there, that little 0, it's pronounced naught. Okay, not very important, but just to let you guys know. You could also call it x0, I think in American terms, that's what we call it. But anyway, it's the same thing as saying our initial, okay? And then this would be our final, okay? All right, so moving on, as we can see here, it can be a positive or a negative value. Okay, and that depends on the direction we're traveling. So let me erase quite a bit of this and let me show you guys what I mean. So say we are, say we are just looking at x-axis, right? Because we're just looking at one dimension, and that's our 0. Okay, and we're here, and we start to move this way. Okay, and we end up right here. Now, we have that our initial position was at 0, and now we ended at 1, 2, 3. Okay, so that is going to be a positive change in direction. Okay, because we went towards the positive x side of the axis. Okay, another thing, we can just say delta x in this case is going to be our final, right, is 3. Whoops. Okay, sorry about that. Our final is 3. Subtract our initial, which is 0. Okay, and so as you can see, that is going to be a positive 3 as our displacement. Okay, all right, but say we're to move the opposite direction and end up here at negative 3, now my delta x is going to be different. Okay, so my final again is going to be negative 3 because that's where I ended, and my initial is 0. Okay, so then my displacement is now negative 3. Okay, so it really depends on the direction in which you are moving. Okay, and typically when we are talking about displacement and distance, we are looking at units in meters. Okay, so that's going to be our SI unit. Okay, now I have a couple of GIFs here to show you the difference between distance and displacement. Okay, now as you can see in this distance one, he starts at 0, he starts walking, he gets all the way to 6, turns back stops here. Okay, so here's my initial, or my x naught. Okay, this is like an intermediate step. Okay, and then this is my final here, or x. Okay, here he does the exact same thing. Starts at 0, goes to 6, and ends at 2 meters. Okay, now our total distance, as you can see, goes from 0 and then adds all the way to 6 and then keeps adding. Okay, and it adds the difference here. Okay, 4 meters. I'm sorry. Well, that is the difference here. It's 4 meters. Okay, adding the 6, that's where you get 10. So that's a total distance traveled. Okay, that's usually what we think of. Now our displacement is going to be a little bit different. Yes, he traveled all the way to the 6 meters and went back to the 2 meters, but when we're talking about displacement, we're just wanting to know how far in total he moved. So he moved plus 2 meters. Okay, and again, this is because he went into the positive x direction. Okay. All right. So quickly going over our graphs of motion. Okay. So we have these graphs, and I'm going to go through them and explain them. Okay. So these are all position versus time graphs. Okay. So on the y-axis, you see the position. On the x-axis, we see time. Okay, on every single one of these. Now, as we look at these, we notice on this first one, our position is just at some constant value. It doesn't change with time. It is just a flat line. Okay, and hopefully you remember in algebra, that means that there is no slope. So our slope here is going to be 0. Okay, now that's important to us because our slopes in all of these graphs tell us something about our velocity. Okay, so when we're looking at slope, okay, typically, when we're looking at slope of a graph, we're looking at a rise over some run. Okay, typically when we're looking at a XY graph, typically our rise is Y and our run is X. Okay, in this case, we are going to take our Y, which is now position, and our X, which is now time. Okay, if you compare this graph to this graph, you can see the similarity. Okay, so now our slope for all of these is going to be our change in position, okay, divided by our change in time. Okay, so we can say delta x divided by delta t equals what? Okay, so hopefully you can think about it. I think I hit on it a little bit in the last module, that speed, what we usually think of as speed is like miles per hour, like driving. Okay, that's what we kind of think of when we think of speed. So this is how you can remember how to calculate velocity as well as speed. Our speed is going to be some distance, okay, divided by some amount of time. Okay, so that's what this slope is showing us. This slope in the position versus time graphs are just a change in position over a change in time, or a velocity. Okay, so going back to over here, if we have our slope is 0, that also means our velocity is 0. Okay, so what does that mean? If our velocity is 0, that means the object isn't moving, right? Okay, so our object is at rest then, okay? Here, in this one, we don't have the slope is equal to 0. The slope does equal something, okay? We do have some kind of slope. What we want to pay attention to is it a positive slope or a negative slope? Okay, so in this case, our slope is positive, okay? So that's all we really care about at the moment, okay? So what this means is that our velocity then is also positive, okay? If we have a positive slope, we have a positive velocity. Makes sense, right? Okay. Now this next one, our slope is negative, so our velocity is negative, okay? And having these straight lines here, these are called, typically in the math world, called linear. Okay, these are linear relations. And they can tell us a little bit more about the velocity. Okay, so if you have a linear relation, that means that the velocity is constant. So that means it's not changing. The velocity is not changing in this case, okay? So say we're driving down the highway and we're moving, okay, in the positive direction. Maybe, let's see, which way would that be for you? Nope. Okay, say that, I cannot think of my, my left and rights right now. Anyway, say you're moving in a positive X direction, okay, down the highway, okay, and you are going 55 miles per hour, and you're staying at 55 miles per hour. This is what your little position versus time graph would look like, something like this, okay, because your position is changing with time. You know, you're going from point A to point B still, but your velocity is not changing. You're going a constant speed the whole way, okay? All right, so moving on to this very last one, okay? This one has a different kind of curve here, okay? It's still, we can't really take the slope of it, okay? At this level, we would need some calculus to do so. But you can see that our position is still changing with time, okay? And because we can't just take the slope easily, we can say that our velocity is not constant. Is not constant. Oops. Okay. When our velocity is not constant, and we'll see this in a little bit as well, the object or you are accelerating. So if our velocity is not constant, we have some kind of acceleration going on. We can't tell exactly what yet, but as we move on, we will understand it, okay? All right. Okay, so going back over velocity and speed real quick, remember that velocity is a rate of change for position with respect to time, okay? And a lot of times in this course, we'll be talking about average speed, okay, which is going to be some distance over an elapsed time, okay? And when we look at average speed, it's going to be V, which stands for speed, equals distance over time, okay? So our speed, we are just going to remember that it is a scalar quantity, okay? Speed is scalar. And our SI units are then going to be meters per second. Okay, and velocity is defined similarly. Let me see if we have that in the next one. Yes, okay. So velocity is defined similarly. Okay, we still have some kind of position and time, okay, but it is defined as so. Our velocity should have a bar on it. Oops. Our velocity, v bar, okay, this is how it goes, equals our delta x over delta t, which we can also say is our x minus x naught. Remember, this would be our final position. This would be our initial position, okay, divided by our t final minus our t initial, okay. Now, again, let's see. Okay, so we will be looking at this in greater depth in OneNote in a second here. Our SI units, again, are meters per second, like with speed, okay, but velocity, remember, is going to be a vector. And that's why I put that bar over the V. This lets you know that it's a vector. Like I talked about in the last lectures in Module 1, okay, you can also put a little arrow like that, okay, that signifies that it's a vector, okay. So let's see here. I do have a couple of graphs here that I wanted to talk about, just like I did in the last slides there for displacement, okay. So our first one here is a, well, all of these are velocity versus time graphs, okay. And in this first one down here, you can see that we have a straight line here at some v, okay, just like we had before in this one, in our position. We had our slope equals 0. So we have that again here. So our slope equals 0, okay? So what does this slope represent though? That is going to be a question that we want to know the answer to, okay? So if we start looking at this, our rise for our graph here, remember, because if we're looking at slope, we know our rise is going to be v, or delta v, and our run is going to be some delta t, okay? Now, we'll talk about this in a few minutes, but a change in velocity over a change in time is going to be our acceleration, okay? So we can look at these other graphs as well. Okay, so sorry, we've got here our velocity is constant, okay, meaning our slope is 0. This implies that our acceleration now is 0, okay? And here's a couple of more examples, okay? Now, let me extend this y or x-axis here, okay? So we have velocity on our y-axis, our vertical axis, okay? And time on our horizontal axis, okay? So this is going to be positive velocity and negative velocity, okay? So if I want to know anything about my slope is positive, right? And that means that my acceleration is positive, okay? And you may think, okay, well, if my acceleration is positive, that means that it's gaining speed, right? Well, not necessarily, okay? So I will get into that in a couple of slides, so hold on to that thought, but that is not quite correct, even though that is very intuitive. That's the way we want to think, okay? So in this case, we have a positive velocity and a positive acceleration, okay? So we have positive v and positive acceleration, okay? Now if I'm looking at this graph, Again, this is positive, this is negative. Now I have a negative negative velocity, okay? And my slope is in the downward direction, right? It's got a negative slope here, which means my acceleration is also negative, okay? Now, even though these two match up, okay, with both of their signs, that doesn't mean that they always will, okay? And I will go into a couple examples with that. Okay, now here is the difference between average velocity, like we were looking at a minute ago, and instantaneous velocity. Okay, so our average velocity is going to be taken over a few different points. Okay, so if we start here at 0 meters and he ends, where does he end? At 14 meters. Okay, our average is going to be that displacement over time. Okay, so our displacement is 0 to 14, so that would be 14 meters. Okay, and our time was 3 seconds. Okay, so if we get out our calculators, okay, 14 divided by 3. Oh, maybe that doesn't say 0. Or maybe it doesn't stop. This animation must be incorrect. So if I'm starting at 0 seconds here at 0 meters, get to 14 meters here at 3 seconds, my velocity overall, I calculate as 4.67 meters per second. Maybe the animation gets cut off or something. It kind of looks like it does right there. So that would be my average velocity. My instantaneous velocity is going to be what the velocity is at that exact moment in time. Okay, so if I were to pause time and take a velocity, okay, that would be the instantaneous velocity. Okay, so a lot of times we are going to be looking at this average velocity since we can't really take the instantaneous in these problems, okay? Unless, of course, there's an unless I can say, actually, we'll get into it in a little bit. Sorry about the confusion. We'll get into it in a little tiny bit, okay? All right, so the final thing is going to be acceleration that we want to look at, okay? So that is going to be our change in velocity with respect to time, okay? So here's my equation for acceleration. And remember that acceleration is another vector, okay? And we say that it's going to be our change in velocity divided by our change in time. So we have our final velocity minus our initial divided by our final time minus our initial time, okay? So say that I have my graph again, velocity versus time. We can see how our slope is going to be our rise, okay? So our rise over our run. So let's see. Let's say this is V for V final, okay? So our rise is going to be V minus V naught over our run, which is 0 to T. So T minus 0. And a lot of times when we are doing these calculations, our T naught is going to go to 0 most of the time, just because it makes this a lot easier. We can also, like in the lab that you'll be doing this week, you can reset the clock watch or the stopwatch for it to just read 0 initially. It just makes our lives a little bit easier. That way we're just dividing by one number down there. Okay, so I can just say this as well. So how much time has gone by? Same kind of thing, okay? Oops. All right. We want to also note our SI units as meters per second squared, okay? And this is just a big note here. If our speed is constant or our velocity is constant, our acceleration is 0, okay? So that's if I have, say that we don't have this line and it's just this line. Whoops, I can't draw a straight line, I guess. But if that was a straight line, okay, then my speed here would be constant, and then my slope would be 0, meaning my acceleration would be 0, just like we saw here, okay? All right, let's see. Now I want to talk about really quick the acceleration due to gravity. Okay, so this is what we feel all day, every day. Okay, and it is represented by a G, typically. Okay, and it is how much speed we gain per second. Okay, so I have a ball. Say I have some ball. Okay, that is being dropped, just dropped. Okay. And my initial time is 0. Like I said, we like to just start the clock right then, okay? And my initial velocity is just 0 because it's starting from rest. And then I let go, whoops. And at some time, t1, okay, 1 second has gone by. I have my new velocity at that snapshot in time as 9.81 meters per second, okay? Or I should just say 9.8. We can put a 0 there instead, like I have here. Okay, so that should just be a 0. All right, so at this time t1, where 1 second went by, now my velocity is 9.80 meters per second. Okay, and again, that is because of our acceleration due to gravity. So for each second, see how it got from 0 seconds to 1 second, I gained that much speed. Okay, so now if another second goes by, if I go from 1 second to 2 seconds, now I will have twice the amount. Okay, oops, oops. Okay, and that's our acceleration due to gravity. Let's see here. I think I skipped a couple of things. I wanted to go into my OneNote and kind of show you guys some examples of a few things. So let's keep that. Let me go over here real quick. I think I kind of did that for you guys. Let's see. Displacement. Yeah, I kind of drew that out for you guys. So it's not a huge deal, but we can go back over it real quick just to get ourselves used to all this stuff. So if I have, I'm going back with displacement. Okay, so don't get confused here. All right, so if I have 2 points on a graph, A and B, and they're representing a car, okay, whoops. Okay, representing a car that moved from A to B. And I want to know my displacement. Okay, so my car at A, my initial position was 2. We can say this is in meters, since usually that's what we go for. Okay, and my position for B, or my X final, is 4 meters. Okay, so calculating my displacement, I will get my final, which is 4 meters, minus my initial 2 meters. Okay, so this car traveled 2 meters, not very far. Okay, And I can do the same thing. If I say that this is point C, D, and E, okay? Let's see, I want to know my displacement from, I want to know it from A to E. Okay, we're going for the big money. All right, so my initial, again, is going to be that 2 meters. My final is now -6 meters. Okay, and remember this positive or negative just tells you where, which direction it is in, okay? So from A to E, my final is going to be -6 meters. Oops. Okay, minus my initial, which is 2 meters. Okay, so my displacement overall from A to E is -8 meters. Okay, and you can practice this. It shouldn't be too difficult since we're only looking in one dimension right now. It should be pretty simple. Okay, now let's see here. I wanted to look at velocity in here. So a velocity example. Okay, so can I move this over at all? No, okay. So say I have some data here. Okay, so this is my little data table. At each time, we have a different position. Okay, and the first thing I want to know is my velocity from A to B. Okay, so changing from position A to position B. I want to know my velocity. Okay, so what I will do, we first need to remember our equation. So our velocity, remember, is going to be some change in x over some change in time. Okay, so I want to look for my final and my initial and my overall time or change in time. Okay, so my final position was 52 meters. My initial, my initial is 30 meters. Okay, my final time was 10 seconds. My initial was 0 seconds. Okay, so doing this math, we get 22 meters divided by 10 seconds. Okay, which gives us 2.2 meters per second. Okay, so that would be our velocity between points A and B. Okay, what if I want to know my velocity between C and F? Okay, we can do the exact same thing. So our velocity is going to be our final position, which is this guy, minus 53 meters, minus our initial position, 38 meters, divided by our time. So we have 50 seconds minus 20 seconds. Okay, and this one I will not be able to do in my head. Okay, I was at 11:91, or can I? No, I can't. Let me double check that. Okay, so 91 divided by 30, we are going to get a velocity of -3.03 meters. Okay, now, meters per second. Notice our, notice our sign here is negative. Okay, now that doesn't mean that we're slowing down or anything. That negative means that we are moving in a negative direction. Okay, so even just looking at these values here, you can see we were at x equals 30, and then at 52, then back down to 38, to 0, to negative 37, to negative 53. So you can kind of imagine, let's see, imagine a graph, whoops, this is t, x, and we started somewhere up here at 30, then we went to up here to 52, okay, then we went down to 38, then we went down to 0, then we went down to negative 37, and then negative 53. So it'll kind of look something like that. Okay, and I know this is super sloppy. I just wanted to give you guys kind of an idea that you can see that the position is changing and the velocity is also changing here. Okay, and it gets to be negative because of that direction. Okay, let's see, where were we? Acceleration. Let me give you guys a quick example of acceleration. Okay, so we know that acceleration, first of all, whenever I see a problem, I start thinking of formulas that I can use. Excuse me. In this example, it looks like we're going to be calculating acceleration of a car. So I want to know how to calculate acceleration. So acceleration is going to be our change in velocity, as we said before, over a change in time. Okay? And we are given that our initial velocity is 10 meters per second, our final velocity is 20 meters per second, our initial time is 0, and our final time is 2 seconds. Okay? So we have v minus v naught over t. Okay? Since our initial time is 0, we don't have to calculate it like we did before here. Okay? Okay. So we have 20 meters per second as our final velocity, minus our initial velocity, 10 meters per second, divided by our time as 2 seconds. Okay, so what is the acceleration? Let's see. 20 minus 10 is 10 meters per second over 2 seconds. That tells us that it's 5 meters per second squared is our acceleration. And remember that it is positive. So that tells us our acceleration is positive. Okay, so we're moving in the positive direction. Okay. Let's see here. Okay, let's get through this last slide and then we'll take a break. Okay, so I want you guys to understand velocity and acceleration together. Okay, so I have a diagram here that shows you a bunch of different car scenarios. And P, there we go. And you can see at the bottom of each that they have these arrows and they are representing velocity and acceleration. Okay, so for each of these, they have a different orientation or direction. Okay, and we want to note these two different scenarios. So if we have a velocity and acceleration that are pointing in the same direction, like we have here and here, okay, that means the velocity is increasing with time, okay? So again, velocity is this is the positive x direction, and the acceleration is in the positive direction, okay, that means our velocity is increasing, okay? Again, here we have our velocity in the negative x direction this time, our acceleration in the negative x direction. Our velocity is still increasing with time, okay? Now, we can talk about why that is. So let's see here. If we have a graph, okay, and this is going to be velocity and time. Remember, our slope of a velocity versus time graph is acceleration, okay? So if my acceleration is positive and my velocity is positive, we will have a graph that looks something like that. Okay, so this is positive, positive, okay? If we have negative, negative, it'll look something like this, negative, negative, okay? Our velocity, if you notice, even though our, it looks like in this direction we're getting more negative and this way we're getting more positive, so this would make sense. Okay, it's increasing with time. But on the bottom side, it is still increasing, the velocity is still increasing, okay? That is because we are really looking at, when we're saying it's increasing, whoops, when we're saying it's increasing with time, we're saying that the magnitude of the velocity is increasing, okay? So these little bars tell me that that's the magnitude, okay, of my velocity vector. And so basically that's saying like the speed, okay? So my speed is increasing. It may be going in a different direction, but it's still the speed, okay, that's increasing. Because when you're reading a graph, remember that this is like 1, 2, 3, okay, this is the same exact thing, but in the opposite direction. And when I take the magnitude, if I say, you know, I'm looking at this point here versus this point, okay, at the same time, this magnitude of V here is 2, and my magnitude on this side is still 2. Remember, these negative values and the positive and the negative signs are really just telling you the direction, okay? So it's not telling you whether the velocity is increasing or decreasing. It's telling you what direction it's moving in. Okay, so I know that that can be a little bit confusing, so maybe let that sink in for a minute, and then I'll talk about when they're in the opposite, okay? So take a minute and then come back to this. Okay, so now if we're looking at the opposite, if we have V and A in the opposite direction, okay, so that's what we have here and here, okay? So that tells us that the velocity is decreasing now with time, not increasing. It is now decreasing with time. Okay, so let's look at our graph again. BT. Okay, so if we have a positive velocity, so we know we're in this quadrant here. Okay, quadrant 1. Okay, maybe you guys remember that from algebra, maybe not, that's okay. Sorry, I have my dog. She's kind of, it's getting late, so she's like, let's go to bed, Mom. Okay, so if we have our velocity is positive, okay, like this one, and our acceleration negative, this, remember that our acceleration is talking about our slope in this case, okay, when we're looking at our V versus T graph. So we will have some kind of negative slope like that. Okay, so that's going to represent our acceleration. Okay. Now, if we have the exact opposite, we have a negative velocity and a positive acceleration. Remember that the acceleration is with slope. So we'll have the exact opposite of this. So we'll be in this quadrant now, quadrant 2, okay, where our velocities are negative, okay, and our slope is going to be positive, so it's going to be going like that, okay. Okay, so, excuse me. Um, just let that sink in, okay, so we have our negative acceleration, positive velocity, and our positive acceleration, negative velocity. Okay, so this is how they will look. They will look very different, okay, from the last one that we were just looking at. Okay? All right, so before moving on, I'm going to have you guys take a break. We're going to come back with another video, okay? All right.